sections 2.1 and 2.2. We are continuing our journey through how to graphically summarize information. We have already talked about how to graphically summarize qualitative variables. So the next topic of discussion, of course, is, sure, you guessed it, how to graphically summarize quantitative variables. Now, there's a lot more than 3. In fact, there was a lot more than 2 ways to graphically summarize qualitative variables. I'm only focusing on sort of the main ones, the ones that we're likely to see in sort of mainstream journalism or in the broad picture of academic research. Now, the 3 main ways to graphically summarize a quantitative variable are frequency tables, histograms, and stem and leaf plots, or as our book I think might call it, stem and leaf displays. So let's take a look at each of these 3 sort of one at a time. A frequency table essentially takes our non-categorical data and breaks it into artificial categories. So for example, right, actual test scores are numeric. You often get a score, say 1 to 100. Now, we tend to conceptualize our test scores as categories. That is, even though you actually might get a numerical grade, say a 73 on your test, most of us in our brain transform that to a category. We say, oh, I got a C. So the idea behind frequency tables is to take quantitative data or a quantitative variable and sort of make it qualitative. That is, break it into categories and then essentially count how many observations fall into each of these categories. Now, when we do this, we have to be careful of a couple things. One, we want our categories to be constructed in such a way that every observation falls into exactly one category. That is, you need to be very direct and concrete. You can't be sort of fuzzy about, well, does an observation fall in this category or that category? Now, I also didn't put it in this PowerPoint, but much like a bar graph, we should make sure that that the categories are of equal width, so that everything's sort of equally represented. So, I hope you brought your permission slips, signed permission slips from home, because we're about to go on a digital oh shoot, I'm blanking on what you call it. A digital field trip. So why don't we all, as a class, go to the Wind Mountain excavation site. As many of you know, this is in New Mexico, and even more importantly, it's a critically important archaeological location for the ancient Native American and Asazi culture. And so what we do as amateur archaeologists is we spend, say, a few months at this excavation site digging up artifacts. And so for each artifact, we record or we measure exactly how far down in centimeters we had to dig to actually find that artifact. And let's say over the course of our time there, we essentially excavate 73 artifacts, or 73, well, our data set, we would say, has 73 observations. Now, keep in mind, right, the variable, the depth, is depth of the artifact, and of course this variable would be quantitative, so this is a good example for what it is that we're talking about. Now there it is. Those are 73 numbers, or 73 depths. What I'm basically saying is, right, as soon as we got there, we dug. We went 85 centimeters, and we said, cool, here's like an ancient Native American arrowhead. And then we went to a slightly different location, and we dug. We went 78 centimeters, and we were like, cool, here's like an ancient Native American ashtray, right? And we did this over and over and over for the 73 artifacts that we excavated, and there's all the depths. Now, I don't know about you, but for me, a PhD statistician who's been doing statistics for close to 10 years, I look at this set of numbers, and it looks like gobbledygook to me. It looks like gibberish. That's the whole point of Chapter 2. The human mind cannot comprehend a big pile of numbers in its entirety, which means that we need a set of tools and techniques to take all that information and summarize it. That's what we're trying to do. So how are we going to summarize this information? Well, let's start with the frequency tables that we talked about. How do we proceed? Probably the most important step to creating your frequency table, and in fact it's going to be an important step to making a histogram or also a stem and leaf plot, is to sort of determine how many categories we want to use. When we're talking about grades on a test, we already have this sort of predetermined sort of cultural convention. We're going to use an A, B, C, D, F system. And we generally know what numbers correspond to an A, what numbers correspond to a B. But if you're talking about taking, say, someone's height and breaking it into categories, it's maybe less obvious how many categories there should be, and it's even less obvious, right, which heights go into which category, right? How do you define a tall category? How do you define an average height category? How do you define a short category? Now, a lot of different statisticians, researchers, computer programmers have come up with these little algorithms. We're not going to get into a lot of detail about them because it's kind of nitpicky, quibbling detail that I don't really think is worth our big picture discussion. But computer programs have a way for a given set of data or a given set of numbers to come up with, say, an optimal number of categories. Now, I put the word optimal in quotation marks because there is not a universally accepted standard way of doing this. Probably every program has a slightly different way of determining what an optimal number is. And probably most of the time these differing approaches will agree on the actual number of categories, but there are certainly situations where they do not agree. And it may be that one computer program gives you a different number of categories than another computer program. Again, this detracts from the big picture. The big picture is that we're going to take this information and break it into categories. Generally, computer programs can do this for us. So I took the information that we had. I asked a commonly used computer program used for statistics called SAS to tell me what sort of the optimal categories should be. SAS broke them into nice, even categories of 30. And it did 1 through 30, 30 through 60, 60 through 90, 90 to 120, all the way to 110. We didn't squint at the numbers long enough, and if I actually scroll back, it destroys all the narrating that I've done. But if you go back at some point, or if you maybe printed up the PowerPoint so you could take a look at the actual numbers, you'll see that the largest number, I think the farthest down we had to dig, was 200 centimeters. So we don't need to go any farther than the 210 category. We actually don't need to go as high as 210, but as I mentioned before, we want to keep our categories the same width. And so to make them the same width, I need to go from 180 to 210 because all the categories have a width of 30. Now, what's the difference between a square bracket and a rounded bracket? Well, the square bracket means that you include that number in the category. The rounded bracket, or the parenthesis, means you do not include that category. So that first category is everything from 1 to 30, but not including 30. And the second category is 30 to 60, including the 30, but not including the 60. The next category is 60 to 90, including the 60, not including the 90. You get the idea? Now, once we have our categories, the next step is both simple and complicated, or perhaps I should say simple and tedious. You, again, go back to those 73 numbers on the previous slide, and you say, okay, how many numbers fall into each of these categories? Now, this is very tedious to do. It's very time-consuming. It's not particularly difficult, right? You could probably bribe, say, your 8-year-old nephew to do this for you. An 8-year-old is capable of doing this. It's just not a particularly intellectually challenging thing to do. And of course, in this day and age, we don't need to bribe small children, right? We have computers to do it for us. And so if we were to count the number of observations in each of these categories, we would see that 4 artifacts were found in the 1 to 30 depth range, 18 artifacts were found in the 30 to 60, but not including 60, depth range. 32 artifacts were found in the 60 to 90 depth range, and so on. So we can see, for instance, that the depth range that sort of has the most artifacts, the most artifact dense depth range is that 60 to 90 range. And then, of course, the next most ones are the ones next to that, right? So the 30 to 60 range and the 90 to 120 range, right? In fact, it looks like the vast majority of artifacts are found between that 30 and 120 range. Now, we can take our frequency table and we can use it to build something called a relative frequency table or a relative frequency chart. The relative frequency table or relative frequency chart, it tells us not the number of observations that fall into a category, but the percent of the observations, or the percent of our sample that falls into each category. Why would we care about that? Well, it's often the relative frequency that's more descriptive than the raw or actual frequency. We can find the relative frequency simply by taking the actual frequency that we had in the previous slide and dividing it by the size of our sample. Easy enough. When we go to the next slide, we'll see how to do it. But before we do so, do you buy into this idea that a relative frequency is more informative often than a raw frequency? Right. I might tell you that, excuse me, I still have a little bit of a cold, that we have Section A of Math 121. It's taught by Professor A. And let's say that we happen to know from, I don't know, how many students failed this class.com, that 5 students failed in Section A. And let's say that 2 students failed in Section B. We might be tempted to say, oh, I should enroll in Section B. Fewer students failed. But again, that's not the whole picture. It could be that Section B, in which only 2 students failed, only had 3 students in the class, which means that 66% of the class failed. There was not very many students in there because, of course, that teacher has a reputation for failing students. And it could be that Section A, that failed 5 students, actually had 50 students in the class, so only 10% of the class failed, right? There was a lot more students in Section A because the students knew that that teacher was an easier teacher than, well, at least than Teacher B, right? The relative frequency is often more informative than the frequency. There's this, it gets me so angry. There's this joke. I don't know. Maybe you've heard it. If you heard it, I hope that you spit in the person's face that told it. Sometimes people say that there's 3 kinds of lies in the world. There's lies, and there's damn lies, and there's statistics. Oh, it just, that slander just eats me up inside. It boils my heart. But it's a little true, right? Statistics sort of has a reputation as, well, you could twist or bend or distort statistics to say whatever you want. A large part of this this slanderous misrepresentation of statistics is this tension between frequency and relative frequency, right? There's a lot of situations where it might be that the chief of police for a town is arguing that crime has gone down, and the mayor of the town is arguing that crime has gone up. And you say, what the cutta? How can it be both? How can crime go up but also go down? It makes no sense, and so statistics is lying to me. But that's not really true, and that's not a fair, accurate way to think about it. In situations like this, where you appear to be getting contradictory information, it is generally the case that one person or party is using the actual frequency, and that the other person or party is using the relative frequency, right? Because if you take population growth into account, it is possible, right, that something like the actual raw number of crimes might increase in a city, but like the crimes per 1,000 people, right, sort of like a relative frequency, has actually decreased. Agreed? And of course, in this situation, most of us would probably want to actually rely on or look at that relative frequency, right? The actual number that takes the population growth into account, whereas the raw frequency, for example, wouldn't. So again, here are our numbers. Before we had our frequency table, we had the 4, the 18, the 32, the 11, 7, 0, 1. Here we just divide them all by 73. I did a little bit of rounding there, but those are the numbers we get. So I could say that 4 artifacts were in the 1 through 30 depth range, but I could also say that about 5% of my sample, about 5% of the excavated artifacts, were found in the 1 to 30 centimeter depth range. Now, we can take these frequency tables, which are pretty interesting and useful in their own right, and we could turn them into something a little bit more graphical, a little bit more visual, a little bit more of a picture and a little bit less of a table. And this is called a histogram. We can either build a frequency histogram, which is based off a frequency table, or we could build a relative frequency histogram, which is built off a relative frequency table. A histogram is essentially a graphical representation of either one, a frequency table or relative frequency table, using bars. In fact, it looks an awful lot like a bar graph that we learned from our last PowerPoint. Nonetheless, it is not a bar graph. The term or phrase bar graph is reserved for qualitative variables. The term or phrase histogram is reserved for quantitative variables. Graphically, we differentiate these two things that would otherwise look quite similar by, as we already talked about, in a bar graph the bars are distinct, they do not touch, whereas in a histogram the bars actually do touch one another. By having the bars touch one another, we are emphasizing the sort of continuous nature of our quantitative variables that are in some way artificially being split into categories. And so here it is. Here is our histogram. I essentially just took the categories and I turned them into bars. So the actual depths are along the x-axis, the horizontal axis. The percent, so here I did a relative frequency histogram. The percent is along the side. So each bar has a width of 30. That was the same as our categories. So for instance, we can see that the most commonly occurring category is that 60 to 90. And it looks like what? About 45%, right? You need to be able to see that. About 45% of all artifacts were between 60 and 90. About 5%, as we already observed, are between 1 and 30, right? And we can see there's really just one artifact way over to the right there. Now, what do we do with the histogram? Why do we care about histograms? Well, histograms can give us some insight into 3 characteristics or properties of a quantitative variable. They can give us a rough idea of center. Center is just a technical term for kind of like an average value. They can give us a rough idea of spread. Spread, again, is just kind of a fancy statistical term for the overall dispersion, the spread outedness, the variability that's present. And third, and really most importantly, a histogram gives us an idea of the shape of a variable's distribution. And so let's talk about the first 2 briefly, and then let's spend considerably more time talking about shape. So here's our histogram for our excavated artifacts. What might we say about center and spread? Right? How might we define an average value, or how might we describe the variability in this data set? I'll give you a couple seconds to think about it. Now, for an average value, I mean, we might say something like 75. 75 is sort of that middlemost bar if we disregard that little blip to the right, that 200. If we disregard that, we kind of have 5 bars. The middlemost bar is the 60 to 90. In the middle of that bar is at 75. So we might say, I don't know, like kind of on average, roughly, the artifacts seem to be found at 75 centimeters. Now you might say, well, the bar to the left of that middlemost bar is larger than the bar to the right, so maybe the mean's a little bit on the lower end. Maybe actually the mean will be a little less than 75, maybe around 70. It's a reasonable answer. You might even just pick that one main bar and say, well, maybe the average amount is between, say, 60 and 90. Right? Most of the artifacts are found in the 60 to 90 range, so it makes sense to say that the average is somewhere between 60 and 90. That would be a reasonable answer, too. What about spread? What about spread? Well, that's the overall dispersion or variability. So looking at this graph, we might say, well, the artifact depths range somewhere from 1 to 210. Now, remember, when we looked at the numbers, we saw that the deepest artifact was 200. But when we're only looking at this graph, we've lost a little bit of information. Looking at that last column, that tiny little last column, the 180 to 210, all we really can glean from looking at that is that there was one observation somewhere between 180 and 210. Looking at the histogram, we do not know what that number was. We do not know where it was. So looking at the graph as a whole, we know that the depths range from 1 to 210. It's one way of saying the variability. Now that 210 seemed to be a fluke. We might say, really, the vast majority of our sample range from, say, 1 to 150. We might even go further still and say that really most of the artifacts seem to be concentrated. We actually made this observation earlier between, say, between 30 and 120. Now, these are useful observations, but I will admit that sometimes they feel somewhat unsatisfying, right? Because your answer might have been a little different than mine. Even the answers that I'm giving are kind of fuzzy, are sort of broad, are kind of big picture, are somewhat subjective. If I asked a class of 30 students to look at this histogram and describe the center and describe the spread, I would probably get 30 different answers. All close to one another, all similar to one another, but not exactly the same, right? That's a little bit unsatisfying. It does leave us wanting something a little bit more clear-cut, a little bit more objective. Right? And we will learn how to do that. That's part of where we're going. We'll see that numerical summaries give us that objectivity that we're sort of looking for. That said, this histogram is very useful to us. Right? Let's imagine that we're at our excavation site. We're what? We're Indiana Jones. How exciting! And after a months-long, harrowing, life-threatening adventure, where over time we've painstakingly excavated our 73 artifacts, and now there's what? There's a passing of the torch, right? There's how do you say his name? There's Shia LaBeouf coming, and we're Harrison Ford, and we're like passing down the mantle of Indiana, right? That sort of weather-beaten hat that sort of signifies our archaeological prowess. And as Shia LaBeouf, the new and up-and-coming Indiana Jones, comes to take over for us, as whoever it is comes to take over from us, what advice might we give them? Right? There is actionable information in this histogram. Right? If we found something at 200, presumably we've been digging every hole to at least 200 centimeters. Who knows? Maybe more. But looking at this histogram, we can tell that seems to be unnecessary, right? Look at our bars. The first one's roughly 5%. The next one's roughly 25%. The next bar's roughly 45%. Let's add that up. 45 and 25 is 70%, plus 5, 75%. If we only excavated to 90 centimeters, we would still have captured 75% of the artifacts we were looking for. The next bar looks like it's close to 20%, right? Maybe more like 15%. So if we actually went to 120 centimeters, it looks like we've captured, what, close to 90%. That is, we can dig almost half as far, say 100-ish, 120 centimeters, which means that we could dig ultimately twice as many holes, right? And if we're digging only to 120 centimeters instead of 200 or further, we're still getting most of the artifacts, but we're wasting less time. We're digging more holes. We're ultimately finding more artifacts, aren't we? And that's what it's all about in the cutthroat archaeological business, is finding more artifacts, right? So when you're getting out into shape, shape, as I said, is the main use of these histograms. It does give us a rough idea of center. It does give us a rough idea of spread. And as I mentioned in a previous slide, right, a picture is worth 1,000 words. The human eye is good at looking at a picture and quickly understanding what's going on, hopefully for us, and using that information to make actionable decisions. To say, hey, wait a minute, whoever's been doing the excavating, I can tell has been digging too deep. Why don't we only dig to 120 centimeters before moving on to a new hole? Oh, I think the other conclusions actually are what I was talking about in terms of how far we're going to dig. So I guess I set myself up for an alley-oop, and I took it a little too early. Now, as I said, probably the number one use of a histogram is to look at it and determine its shape. So before we can talk about that, we need to understand what the different sort of shapes are that a histogram can take. The four main ones that we're going to focus on are symmetric, skewed, bimodal, and uniform, and then we'll see that there's actually two different types of skewness, or two different types of skewed shapes that we can look at and consider. So this is an example of a symmetric distribution. A histogram like this might occur if you recorded all the SAT scores on the math exam for, say, all the seniors at your high school, and if you made a histogram of their scores, that kind of looks kind of roughly almost like a bell shape, right? And if you kind of split it right along those two tall middle columns, it's not exactly symmetric, but if you were to split it between those two columns and kind of fold the two ends together, they would come close to matching up, wouldn't they? Right, particularly if you look at those two middle columns and you go one column out, those two columns have pretty much the exact same height, and you go out further, those columns have almost the exact same height. You go out further, those columns have almost the exact same height, and even the two middle columns are very close to the same height. Right? So kind of the sort of right half of this thing is sort of symmetric, or matches up with the left half. So SATs, for instance, they're man-made standardized tests. A lot of standardized tests are created in such a way to force the histogram of scores to look something like this. Probably the next most common type of shape is something called a skewed shape. Skewed just means it's not symmetric. There's no axis of symmetry. There's no point that I could sort of cut it and fold it over and the two ends will match up. Now this is an example of something called a right skew, right? It has this tapering tail that goes off to the right. This occurs quite a lot in real life. For instance, it occurs a lot with salaries. Now, the way the computer did the scale, along the bottom. So along the bottom are the actual salaries. That where it says 2e plus 05, it's just saying take the number 2, and add 5 zeros is essentially what it's saying to do. So that would make it, I think, what would that make it? 200,000, I think is what it's saying. So it looks like our thing ranges from 0,000 to 200,000, 400,000, 600,000. And so most people's salary are far to the left. Most people are making, I don't know, $50,000, $60,000 a year. There's a little less people that have been working at their jobs for a while. They've maybe accrued some salaries. There's a smaller bar representing them, hence a smaller frequency, smaller percentage of people that maybe make 80,000, 100,000. Right. By the time we get to 200,000, the bars are fairly small. There's not a lot of people that make $200,000. You probably have to be, one, in the right profession. So maybe you're like in the financial profession. Or maybe like you're an engineer, a computer scientist. You're in something that's a financially lucrative profession. And maybe you worked at your job for a while. Right? You get to 400,000, that's even rarer. Right? Again, maybe you're someone that works in the financial district or the financial sector, but you've gotten a lot of raises. Maybe you're a vice president or something. Not a lot of vice presidents in the world, but a handful of them, and they're making in that 400,000 range. Right? And that tail, in theory, keeps trickling out, right? There's people that make millions of dollars per year, right? Some CEOs, some professional athletes. Not a lot of them, right, relative to the rest of us. A very, very minuscule percent of, say, all people in the country or even all people in Philadelphia, right? Something like 0.0001%. But there is some people that make millions of dollars. And that creates that tapering out tail effect. If we went through, right, the sort of general Philadelphia region, and we recorded, say, the assessed value of all the homes, and made a histogram of the home values, we would basically see almost the exact same histogram. Does that make sense to you? Right? You would have all the bars to the left. They would be the larger bars, right? I'm not entirely sure offhand what the actual assessed value of that house would be, but it would be all the people that make roughly $60,000 a year are all living in, say, quote, houses that would be affordable for a $60,000 salary. And then the people, much, much, much fewer, right? The smaller proportion of people that make $200,000 per year, they're living in, right, a smaller proportion of $200,000 homes, right? And again, that tapering tailed off effect. Handful of people make millions of dollars. Excuse me. And so a small handful, 0.001% of all homes, say, would have an assessed value of millions of dollars. Does that make sense? Hopefully so. Now, the opposite of right skew is called left skew. So, left skew, we can see, has that tapering tail. The tail actually tapers off to the left, not to the right. In my personal experience, left skew occurs a lot less frequently than right skew. Of all types of skewness, in my experience, right skew is the one that occurs most often or most frequently. Now, what I've read is that lifetimes of electrical components, or like light bulbs, things like that, tend to follow a left skewed distribution. So if that's true, right, then that means all the actual amount of time that a light bulb burns is maybe really close to what it says in the package. And so there's a sort of clumping up. All the larger bars, right, remember the height of the bar sort of says the percent or proportion of times, the percent or proportion of our sample that actually lasts that long. So most of our sample lasts however long the package says it will. Now, since it's left skew and it tapers off to the left, that means not very many last longer than what's said. In fact, it's more likely it lasts less long. And then we have that sort of tapering off effect to the left, whereas, right, it's very unlikely that a light bulb will only last a day or two, but we've all, I think, had examples maybe where we put a brand new light bulb in and we come back a day later and the bulb's burned out. Happens a small, very small proportion of the time, but it can happen. I'm not so sure I buy into the fact that light bulbs really work that way, but right, if they did, that's what a left skewed, say, distribution would look like. Now, another shape is something called a bimodal shape. So a bimodal shape just means that the histogram has two peaks or two humps to it. So it turns out that if we were to, say, take a sample of a bunch of Westchester students and ask them what their heights are and record their heights and make a histogram out of it, that it would have this kind of weird shape to it, this shape that has two peaks. Why is that, you think? Why does it have that weird double hump shape? Exactly. It's because we have sort of two subgroups, right? We have males and females. On average, males tend to be taller than females. So that rightmost peak is actually corresponding to really sort of the average height of males, whereas that leftmost peak is corresponding to the average heights of females. This is actually a very important use for histograms. Is looking at the histogram helps us determine whether or not there are sort of subgroups or subpopulations that in practice need to be separated and analyzed separately. Right? If we were to try to ask the average height of a Westchester student, we'd get what looks like the peaks are right around 70 and 65. So if we asked like the average height of a student, we'd get something like 67.5, right, between those two peaks. But that's sort of a weird nonsense number, right? That doesn't actually represent anyone that well. It kind of lumps the males and the females together, right? A more accurate way of describing the average heights of females is to say, well, males tend to be around 70 inches tall, whereas females tend to be around 65 inches tall, right? That bimodal shape is communicating to us that there's two subgroups, and to do an appropriate statistical analysis, these two subgroups should be separated and analyzed separately. Now the last type of histogram is something called a uniform. A uniform histogram is really just, if it's exactly uniform, all the bars would be exactly the same height. What we see in real life is more along the lines of something that might be, quote, roughly uniform, which would mean that all the bars are roughly the same height, which is what we can see here, right? If I took a six-sided die, for instance, and I rolled it, say, let's say I rolled it 6,000 times, and I made a bar for how many ones I rolled, and a bar for how many twos I rolled, and a bar for how many threes. Do we know what kind of shape we would expect that to have? Yeah, good. Right? We'd probably expect it to have a uniform shape, right? I forget how many times I said I rolled it. What, 600 times? So I would expect roughly 100 ones and roughly 100 twos and roughly 100 threes. Now in reality I'd probably get something like 110 ones and maybe 94 twos, but they're going to be close to one another. And so that their overall histogram would have this uniform shape to it. Now let's go back to our histogram. What do you think its shape is? I think that I am personally leaning towards right skewed. It looks like it's a little steep to the left. Looks like maybe it has a bit of a tapering tail effect going out to the right. If you had sort of ignored that 200, because it's just one observation that seems to be a bit of a fluke, if you had sort of ignored that and focused on the 5 other bars and you said it was roughly symmetric, I don't think I would count that wrong. I personally prefer right skew, I think, looking at this, but I don't know that symmetric is like egregiously wrong. It's definitely not left skew. It definitely does not have a tail tapering out to the left. It's definitely not bimodal, and it's definitely not uniform. So again, I feel right skew would be sort of the perfect answer. If you went with symmetric, I wouldn't argue with you too passionately. Now, as we get ready to wrap up this PowerPoint, which is going to essentially wrap up graphical summaries, I want us to talk a little bit about the disadvantages of histograms. We've already seen that they're useful, right? We looked at our archaeology example, and right, we made an actionable decision that we shouldn't be digging 200 centimeters. We shouldn't be digging more than, say, 120 centimeters. But there are disadvantages to these histograms as well, right? The first is that it's sometimes hard to pick the right number of categories, right? There's not even a clear-cut way to determine what the right number of categories are. You might do a histogram on one computer program, and it says to use 7 categories, and then you use the exact same data on a different computer program, and it uses 8 categories. You cannot say that the 7 is right or wrong, or that the 8 is right or wrong. And most of the time, the histograms will look pretty much the same, but there are situations where changing the number of categories can change the look of the histogram quite a bit. Right? And so there's something unsatisfying about that. As we also mentioned, they only allow us to make broad, subjective statements. Now, this weakness here, we're going to address that in our next PowerPoint. In our next PowerPoint, we're moving from, right, these pictures that allow us to make very quick but somewhat subjective broad statements to numerical ways of summarizing our data, which allow us to perhaps make slower decisions that instead of using our naked eye, we instead use a calculator, but decisions that allow us to be much more objective, and also statements or decisions that are made using these sort of ironclad rules or conventions in such a way that we kind of all would come to the same answer or conclusion, right? That is, that allows us to actually have answers that are, for instance, quote, right. Now, the last sort of disadvantage or weakness of a histogram that I want to talk about is that a histogram only shows how many observations fall into each category, not what those observations are. Right? We talked about that with our excavation histogram. We said that we can see that there was one artifact between 180 and 210, but looking at the histogram, we couldn't tell. Was it closer to the 180 or was it closer to the 210? That's a disadvantage of all summarizing, right? If you summarize, you are by definition losing some information. Now, that last weakness can be addressed by something called a stem and leaf plot or a stem and leaf display. A stem and leaf plot is a fancy, more descriptive version of the histogram. However, this extra description comes a little bit at a cost. It's more difficult to make, and it looks very cluttered. It's not particularly aesthetic for large samples, which means that it's mostly used or mostly appropriate for situations where we have a relatively small sample. So here's an example of a stem and leaf plot. A survey was conducted to gather ratings of the quality of service at a local restaurant at Westchester. I'm not going to tell you which restaurant it is. I want to preserve anonymity. Respondents were asked to rate their overall experience or their overall service using 0. 0 is horrific, and 100. 100 is as good as it gets. And the information is in the stem plot. The stem plot is listed below. I often do put a question on the test involving stem plots. So it is important that you get a sense or a feel for how this works. The numbers to the left, the 3, 4, 5, 6, 7, 8, 9, the numbers to the left are called the stems. they essentially are the categories. So that 3 is really corresponding to 30s. That 3 is the 30s category. That 4 is the 40s category. That 5 is the 50s category. So the stems are the categories. The numbers to the right are called the leaves. They're the numbers that you pair with the stem to get the actual observation. So let's go to the 30s. Let's go to that top row. There's a 2 there. That 2, it pairs up with the 30 to create the value 32. It's saying that somebody rated the restaurant 32, and in fact, that's the lowest rating the restaurant got. The other 2 observations are a 34 and a 35. So there were 3 people who rated the restaurant in the 30s. Someone gave it a 32, someone gave it a 34, someone gave it a 35. Does that make sense? Let's start with this. Did anyone give the restaurant a rating of 67? Good. The answer is no. Nobody gave it a 67. I can see that by looking at the 6th row, right? Or the 60s category. Someone gave it a 61. 2 people gave it a 62. Someone gave it a 65. Someone gave it a 66. But nobody gave it a 67. Similarly, no one gave it an 80 anything. Agreed? That 80s column is completely, or 80s row, sorry, is completely empty. What was the most common rating? Ah, very good. You're a stem and leaf expert. The most common rating, as you already said, is 51, right? There were 3 patrons or 3 diners who gave their overall experience a 51. Do you see what I'm saying, or what I said in the previous slide, that this really is kind of like a histogram? If you were to take this picture, I wish you could see my hand right now because it's sort of doing what I'm talking about. If you could sort of pivot that so that the categories, instead of being stacked up vertically, were instead sort of lined up on the bottom of this plot, it would look more like a histogram, wouldn't it? With the 30s category, 40s category, and the length of the row instead would be the height of the bar, which would tell us how many observations are in that category. Just out of curiosity, try to do that with your mind. Try to pivot it to the left, and sort of look at this as a histogram where each row is now a bar. What would the shape of this stem and leaf plot / histogram be? Good, good, very good. I agree. I think it has a little bit of a right skew to it as well. Right? You got a little bit, everything seems clustered along those low values, and you got this sort of tapering tail effect thanks to the 70s and that one person, maybe the owner's son or daughter, who gave it a 92. Now again, if I were to ask you something about the average score, the spread of scores, you could give me kind of an uncomfortably broad statement, right? That's maybe not quite right, but not quite wrong. But as I said before, there is a lot of information here. Let me hopefully prove it. Would you eat at this restaurant? Yeah, I wouldn't either, right? And we can make that decision, that important decision, really in a split second by looking at this graph and understanding what it's telling us, right? Almost all of the scores are in the 30, 40, 50, 60 range, right? In terms of at least school, that's a failing grade. Why would you spend your hard-earned money at a restaurant who's getting essentially an F? Right? So again, we definitely are left wanting something a little bit more rigorous, a little bit more objective, a little bit more black and white. There's no doubt in that, and that's where we're going in terms of our Chapter 2 discussion. But all that said, there is a lot of usefulness, there is a lot of utility to these graphical summaries. We can look at the stem and leaf plot, and if we understand how it's working, come to a very quick decision to say, heck with that, I am not going to that restaurant. And that said, I am very thirsty and parched from all this narrating and all this talk of restaurants. I am going to conclude this lecture, and I'm going to go treat myself to a Rita's water ice. You may or may not do the same, depending on whether it's winter or summer that you're actually listening to this particular PowerPoint.